All right, so we have example number 3 for the work energy theorem. An elevator cab of mass m of 500 kilograms is descending with a speed v initial of 4 meters per second when its supporting cable begins to slip, allowing it to fall with a constant acceleration a equals g divided by 5. So our acceleration will be equal to 9.8, which is g divided by 5. So if we do that really quick on our calculator, 9.8 divided by 5, we get 1.96 meters per second squared. So that's our acceleration downward. So A, it says during the fall through a distance d of 12 meters, what is the work done, W sub g, on the cab by the gravitational force F sub g? So if we draw a free body diagram, we have the force of gravity down, and then it's an elevator, so we'll call that the tension force upward. Now we are accelerating downward, and we want to know the force done by the work done by the force of gravity. So we know that work is equal to force times displacement times the cosine of theta. In this case, we're talking about the work done by the force of gravity, so that will be the force of gravity times displacement times the cosine of theta. So of course, our displacement is also down, so that angle is going to be 0 between the force of gravity and the displacement vector. That angle is 0 between those two vectors. Force of gravity, of course, we know is mass times acceleration of gravity. We also know what displacement is, so now we can plug our numbers in and find the work done by the force of gravity. So we get work done by the force of gravity is equal to mass, which is 500 kilograms, times the acceleration of gravity, 9.8 meters per second squared, times displacement, which was 12 meters, times the cosine of 0, which of course is just positive 1. So we get 500 times 9.8 times 12 times positive 1. And we end up getting that the work done by the force of gravity is equal to 58,800 joules. So that's our answer to A. And then it says B, during the 12-meter fall, what is the work done on the cab by the upward pull T of the elevator cable? So of course, we're going to use the same equation to find the work done by the tension force. However, we don't know what the tension force is. So first and foremost, we have to calculate the tension force. So, oh, that's not C, it's B. So we know from Newton's second law, net force is equal to mass times acceleration. I'm going to call downwards positive here because that's our direction of acceleration. So I get the force of gravity minus the tension force equals mass times acceleration. So solving for tension force here, we get tension force is equal to the force of gravity minus mass times acceleration. So of course we know force of gravity is equal to mg. So we get mg minus ma. Tension will be equal to mass, 500 kilograms, times acceleration of gravity, 9.8 meters per second squared, minus that 500 kilograms, times the acceleration of the elevator, which we found to be 1.96 meters per second squared. Running out of room, as usual. So we get 500 times 9.8, and then we're going to subtract 500 times 1.96 from that. And we get 3,920. So that is our tension force. Now that we have our tension force, now we can find our work done by the tension force. So we have work done by the tension force will equal the force of tension times displacement times the cosine of theta. Now we know tension force is 3,920. We know the displacement is 12. Now that angle there is going to be the angle between the tension force and the displacement. Now the tension force is upwards, but our displacement is downwards. So that means our angle is going to be 180 degrees, and the cosine of 180 is a negative 1. So we're going to get negative work done by the tension force. And that makes sense because that tension force is going to be taking away some of that energy, right? Slowing the elevator down. So we get work done by the tension force is equal to the force of tension, 3,920 newtons, times displacement, 12 meters, times a cosine of 180 degrees. So we get 3,920 times 12 times the cosine of 180. And we end up getting work done by tension is a negative 47,040 joules. So that's the answer for part B. And then part C, it says, what is the net work done on the cab during the fall? So the net work is just going to be the sum of both of those works that we just found together. So for part C, net work will be equal to the work done by the force of gravity plus the work done by the tension force. So our net work will be equal to work done by the force of gravity, which we found to be 58,800 joules, and then plus a negative 47,040 joules for the work done by tension. So to this, in my calculator, I'm going to add 58,800, and I get the net work done is equal to 11,760 joules. And then finally for part D, it says, what is the cab's kinetic energy at the end of the 12-meter fall? So I know for part D that the net work done will be equal to the change in kinetic energy. So I want to find final kinetic energy here. So I get net work, whoops, not you, is equal to final kinetic energy minus initial kinetic energy. So I'm going to add initial kinetic energy to both sides, and I get final kinetic energy equals work net plus kinetic energy initial. Now we do have an initial kinetic energy because this elevator is traveling at 4 meters per second when we start the fall. So I am just going to take my net work done, 11,760 joules. And then what we're going to do is we're going to use the kinetic energy equation to find initial kinetic energy as well. So we get 1/2 times the mass of the elevator, which is 500 kilograms, times initial velocity, which is 4 meters per second, and we square that. So we get 11,760 plus, open parenthesis, 0.5 times 500 times 4 times 4, close parenthesis. And we end up getting kinetic energy final is equal to 15,760 joules for our answer. Now, of course, for this last part D, of course, there's a bunch of different ways to find the final kinetic energy. Because you know acceleration, you could find, using kinematics, you could find your final velocity and then therefore find final kinetic energy using 1/2 mv squared. That's totally possible as well. So like in all physics problems, there's usually a bunch of different ways to do these problems. But that way for part D that we did is the easiest because we already knew the net work done from part C. So that's kind of why I used the work energy theorem to solve part D.